Performance optimization of wavelength conversion of high-order QAM signals. It is well known that for high-order QAM signals, the increasing number of states in the constellation makes them more sensitive to the intensity and phase noise. Previously, power penalties of around 4 dB at 5 GOD, and 2 dB at 21 GOD were experimentally demonstrated for the converted 64 QAM at bit error rate, BER, of 10-3. As shown in Figure 3, to implement the AWOC for high-order QAMs, a simple degenerate FWM in HNLF is deployed. Input QAM signal serves as probe, while a CW pump works as pump in AWOC. The phase of the converted signal follows the phase relationship, theta idler equals to theta pump minus theta probe, where theta idler, theta pump, and theta probe are the phase of the idler, pump and probe, respectively. In order to implement an AWOC for QAM signals with minimal power penalty, the phase and intensity noise from both pump and probe should be suppressed. Since high-order QAM signals are sensitive to the phase noise in the system, to avoid the introduced linear phase noise from pump, it is preferred to deploy narrow-linewidth light sources for the pump source. In the following experimental demonstration, a tunable external cavity laser, ECL, with the line width of around 100 kHz is employed as the light source of the input QAM signal, probe. On the other hand, 2 fiber lasers, FLs, with a line width of around 10 kHz are used as light sources for pump and local oscillator, low, at the coherent receiver. Since a narrow linewidth FL was deployed as pump source, the linear phase noise from pump was negligible. Operation principle of wavelength conversion using FWM in HNLF. In the AWOC subsystem based on FWM in HNLF for high-order QAM signals, the main nonlinear distortions in the converted signal are mainly from the following sources. SPM from the probe signal, since the input QAM signal, i.e. the probe, exhibits multilevel in amplitude. In the nonlinear operation condition, the probe may experience SPM. The nonlinear phase noise will then be transferred to the converted signal through FWM and finally deteriorate the converted signal. Therefore, it is critical to manage the launch power of probe to avoid the degradation in the converted QAM signal caused by the probe-introduced SPM. However, it will sacrifice the conversion efficiency. There is a trade-off between conversion efficiency and the quality of the converted signal in the performance optimization. XPM from the pump signal, as discussed with limited optical signal-to-noise ratio, OSNR, in pump, the amplitude noise in pump may distort the converted signal by introducing nonlinear phase noise through XPM effect. In our experiment, a FL is used as the pump source. Thanks to the low relative intensity noise, RIN, of the FL, the OSNR of pump source is measured as around 57 dB, which avoids the pump-induced nonlinear phase noise. SBS from the pump signal, in AWOC subsystems based on FWM and HNLF, SBS limits the conversion efficiency unless the pump's line width is broadened to increase the SBS threshold. In an AWOC based on degenerate single pump FWM, if intentionally applying phase dithering on the pump, it will deteriorate the converted QAM signals. Although it has been shown that the phase dithering could be compensated for at the coherent digital receiver by DSP, the applied phase dithering will be accumulated in the converted signal as distortions and be further transferred to the next node, which is not suitable for multi-hop optical networks. In our experiment, thanks to the short length, 150 meters, and high nonlinearity, nonlinear coefficient, 18/W/km, of the deployed HNLF, the measured SBS threshold is around 24 dBm, which allows a high launching power even without applying additional phase dithering. However, the optimization of the pump power is required in order to avoid the SBS distortion in the pump. As discussed above, the main undesired nonlinear components in the AWOC based on degenerate FWM and HNLF are from SPM of the input QAM, probe, and SBS of the CW pump. In order to eliminate these deleterious components in the converted signal, the launched pump and probe power should be well managed. Depicts the experimental setup used to achieve the AWOC of 36 QAM and 64 QAM through FWM and HNLF. Since high-order QAM signals are sensitive to the phase noise in the system, it is preferred to employ narrow linewidth light sources in the experiment, especially for the pump source. Owing to the lack of instruments in the lab, in the experiment, a tunable ECL with a line width of around 100 kHz was deployed as a light source of the input QAM signal in the experiment, whereas two FLs with a line width of around 10 kHz worked as light sources for the pump and low at the coherent receiver. To synthesize optical QAM signals, the light from the ECL, operating at 1551.38 nanometers, was modulated by a single in-phase/quadrature.